Hi, I'm Doug Hooton. I'm a professor at the University of Toronto, and my specialization is concrete materials and durability of concrete. I did my undergraduate and master's here at Toronto, and then I went to McMaster and did a PhD. And then I worked for Ontario Hydro's research division through the 1980s. And then in 1986 I came back to the university and started working in concrete materials here. We've got almost 20 graduate students in the materials area, and there's 3 professors, and it's quite gratifying to see the growth in the work that's being done. Courses I teach are on concrete materials. I teach the Civ 209, the Introductory Civil Engineering Materials course, in the spring of second year. I teach an elective concrete technology course, 514, in the fall of fourth year, which is open to both master's students and fourth year students. And I teach 2 graduate courses. I teach an instrumentation methods course for all the specialized materials instrumentation we use for analysis, and every second year I run a chemistry of cement course, bringing in outside speakers from around the world, and we run a large international audience for that. For the chemistry of cement course, I typically bring in 5 or 6 speakers, a number from the US and from Europe, and we bring in, that attracts students from Europe as well. It's a RILEM accredited educational course, so RILEM is mainly a European standards organization, and we've had students coming from various countries, Denmark, Germany, France, come attend the courses, in addition to North American students from 15 or 20 different universities. Well, my research is funded by NSERC and the Ontario Ministry of Transportation and various state highway agencies in the US, but a significant amount of my research is funded by industry, most of it through the cement industry, through the Cement Association of Canada, the Portland Cement Association in the US, or individual cement companies who fund, I say, the bulk of my research. And my research chair in concrete durability and sustainability is funded jointly by NSERC and the Cement Association of Canada and Holcim Canada. I got involved with standards back when I joined the power company, Ontario Hydro, back in 1981, because we were just starting to build the Darlington nuclear plant, and so I got involved with the standards related to all the cement and concrete materials that were used at Darlington. And so I had to look at both ASTM and Canadian standards for materials and meet those specifications. So I got heavily involved with the standards and got heavily involved with especially ASTM at that time, and later with CSA standards. And I'm now a member of over 40 different standards committees in the US, Canada, and a few in Europe. And I've chaired a number of committees. I chaired the ASTM Concrete Committee, C9, for 6 years. Got well over 1,000 members. And I've chaired the Canadian standards for cement. Now vice chair again 10 years later of that committee, and I'm vice chair of the ASTM Cement Committee, which has about 500 members, plus member of individual technical subcommittees on very technical subjects. Currently I'm chairing sulfate resistance at ASTM, concrete's resistance to its environment, which is freezing and thawing and scaling, and I chair a committee on paste performance, which is about cement admixture interactions, because concretes now are more complicated. It's not just Portland cement and water, there's supplementary cementing materials, there's blended cements, there's mineral fillers, there's a myriad of concrete admixtures that get involved with it. Sometimes these things don't get along in terms of the expected things that happen on a job site. Getting workability, maintaining workability, getting proper air content. So we're trying to develop standards, and we've developed 2 so far that allow us to predict that performance before it actually ends up in a truck. When I started here, there wasn't very much in terms of concrete materials facilities, so now we've built a fairly large lab. This is one of about 4 or 5 labs we have in the building, and this one has some of our analytical tools in some of the side rooms, and we've got some of our durability test equipment out here behind me in the lab. We do our casting in 316 mortars, and we have our environmental chambers, freezers, and those sorts of things, ovens in that room. Down in the basement we have a petrographic laboratory together with Professor Carl Peterson, and we have our concrete mixing in the basement. We have environmental chambers in the basement for various durability type testing. So we're spread out, and we've got about 20 graduate students working in concrete materials at the present time. So a lot of the stuff we do is either on, at least that I do, is on cement materials, trying to improve cementing materials because they're evolving with time, especially with sustainability issues. We're using a lot more Portland cement replacement materials. We're using interground limestone now, Portland limestone cements, and we're trying to study the impact of those on their properties of concrete and durability of concrete. And then we're doing specific durability research as well, related to things like freezing and thawing resistance, de-icer salt scaling, chloride ingress that initiates corrosion of rebars, alkali aggregate reaction, and a lot of work on sulfate resistance. So we cover all the bases on durability, and we're doing things like volume change. We're doing work for the Ministry of Transport now on transverse cracking in high-performance bridge decks, which they're concerned about. So Eric Liu's doing his research on that part of the project, trying to minimize volume change by making adjustments to the concrete mixtures to evaluate whether these high-performance mixtures do indeed have higher volume change or not. At that point, it's not clear yet. We're also working on something as simple as optimizing aggregate properties in concrete. The aggregate specifications in Canada and the US haven't changed in 100 years. And so they're not optimized. They work, but it's amazing if you change the aggregate property, do something as simple as putting an intermediate size in to remove a gap in the middle of the gradation analysis, then you can save 10 to 15% cement, which then has impacts on sustainability, energy, and CO2 emissions related to concrete production. So, because 90% of the CO2 emissions and energy associated with concrete are from the Portland cement production. So if we replace cement or total binder content, or we replace part of the Portland cement, we can have a big impact on sustainability of the concrete industry. And that's one of the reasons that they're supporting the research we're doing. A lot of our research impacts on standards. The sulfate resistance work we've done with the Portland limestone cements has led to new specifications or standards for low temperature sulfate attack because of the particular concerns with limestone cements. The work on alkali aggregate reaction that is being done is addressing deficiencies in the Canadian standard and in the US standards for ASR mitigation in concrete. One of the students is working on trying to measure water-cement ratio of fresh and hardened concrete, because we specify water-cement ratio, but there's no method to measure it. There's no standard for measuring water-cement ratio. And of course, how do you evaluate that? So we're trying to develop methodologies that are reasonably accurate for that purpose. And we're developing new test methods related to durability in terms of measuring the penetration resistance of fluids into concrete. We have great facilities for measuring the permeability of concrete, water through concrete, or for gases or vapor through concrete. We have all the standard methods. In fact, we helped develop a lot of the standard methods for chloride ingress for concrete in ASTM and CSA. We're now looking at fast techniques, resistivity methods, electrical resistivity methods that are simple enough, if we're trying to standardize them now, that we can measure resistivity on concrete on the same cylinder that's going to be tested for strength. So you get some measure of its durability in addition to its strength, which would improve the standards. If we make it really simple, within a minute you can take the same specimen and turn it into and then use it for concrete. So there'd be little work for the industry, but they get a lot of extra information from that. Some recent Toronto-based projects, I was involved with the service life modeling and the durability related things on the parking structure at the new Pearson terminal, and now on the TTC subway expansion project. We've helped write a specification, a performance specification for the TTC, and we've also worked with some of the contractors on how to achieve that specification on some of the mass concrete structures for these big stations. The other thing I get called about every time something falls off the Gardner, I talk to the media about that, because it's a case of where they've got to decide what they're going to do with that structure. And I think rather than just doing mild fixes. They need to do some more permanent fixes on that structure that has probably gone past the point of marginal fixes. My research is published in some ACI Materials Journal, Cement and Concrete Research, Advances in Building Research, Cement and Concrete Composites, Construction and Building Materials, and the Canadian Journal of Civil Engineering. In addition, a lot of my work is published in conference proceedings. I attend a lot of conferences internationally and on durability and sustainability in particular. Now, one of the things we do that's a bit different is we take a material science approach to materials research. We're not just testing concrete for slump and air and strength and even physical properties, but we're trying to understand what's going on at a micro or even a nano level. So we have analytical tools, we have access to chemical analysis procedures, we can even squeeze the juices out of concrete to look at the chemical analysis of what's in solution. And then we want to know what's going on with the chemistry and mineralogy of what's in the solids so we can predict future performance because of the interactions. And we want to understand the microstructure of the material, and the scanning electron microscope and X-ray analysis equipment that's attached to it allow us to get down into a low magnification. We have optical microscopes, we can do thin sections for the macro look at materials, but then we can go down to a micro, submicron level to look at the nanostructure of the material and to analyze it. So anything we look at, we can do a chemical analysis of what we're looking at to confirm what it is. And then we do mineralogical analysis, which is in another laboratory where we do X-ray diffraction work and thermal analysis so we can determine not only the chemistry and the morphology that we see here, but we can look at the mineralogy, what is the phases that are there, because it's the phases that are transforming that result in some of the durability issues that we're concerned with. We do a lot of work for the cement industry on things that impact on their fresh properties of cements. So we do heat of hydration calorimetry. We have isothermal calorimeters where we can look at small changes in the cement composition on how cement sets and hydrates. And then we can complement that with some of the other equipment in this room. We can do X-ray diffraction to look at the mineralogy of what's happening in a few minutes' time. We can stop hydration and look at the phases that are forming that influence setting time and slump retention. And we can do thermal analysis to look at some of the phases that are forming as well to confirm the analysis. And in addition, we've got tools here to look at vapor isotherms. We can look at this because hydrated materials have high internal surface areas. They're surface active materials. So we want to know how vapor is held on them at various humidities because it impacts on the durability issues. So we can run through a vapor desorption, sorption isotherms. So we have a number of tools that can complement each other to give us a whole bunch of information on what's going on, either at early age hydration, or we can do work on later age properties, or we can look at long-term durability. We can use these same tools to look at deterioration of cements and concretes with time in aggressive environments. Well, concrete's the most widely used material in the world, and it's not going away soon. It ends up resulting in about 5% of the CO2 and energy use in the world, but it's one of the lowest per unit energy and CO2 producers, but it's just so much of it used that it ends up being that large quantity. So the industry is still looking to reduce that footprint, and so we're doing research on the mineral fillers, the cement replacement materials, and optimizing aggregates and using chemical admixtures to make better concrete with smaller environmental footprints that will also be durable, because the more durable a structure is, the less impact it has on its life cycle.